So in this hour, we are going to talk about the fourth handout, and which is talking about the bipartite graph. Oh, and maybe this word I did not mention that, right? Bipartite just means that it has two part. It is an adjective. Okay, so it is an adjective. 形容词. Okay. It has two part. And the Chinese translation does not really make too much sense, but it is just a mathematical concept that it is not too hard. So we will start with the definition, and then we will see how to use the adjacency matrix to see this structure. Okay, so let's start with the formal definition. A simple graph, G, is a bipartite graph if its vertex can be partitioned into two parts. If the vertices can be partitioned into X and Y such that all the edges are in between. So this is a bipartite graph. For example, we got C4. We can partition that into left and right. And so this is X. And this is Y. So that X and Y has no common vertices, but all the edges are in between. So I'm going to write down the formal definition. Okay, so that's pretty much what I described before, and I used a particular a spatial notation that is X dot union Y, and whenever you see this kind of dot, it is not really standard, but people means that it is the union of X and Y, but meanwhile X and Y has no intersection. So which means it is a partition. Okay, and we have see some example on the top right, and let's try to see one more example. This graph is called the hypercube Q3, and if you draw that in a different way, you will see that it is basically looks like the skeleton of this cube. Right, so we call that as a hypercube Q3. Okay, so Q3 is actually a bipartite graph, and the way to see that is the following. We pick one vertex and write a 1 on there. We are going to find out, okay, maybe let me just write it as X, okay, lowercase x. Okay, now we look at X and look at all the neighbors of X. If it is a bipartite graph, the neighbor of the neighbor of an X vertex is all the vertices in Y. So it is supposed to be in Y. And the neighbors of Y is going to be in X, and including this one, and the last one is Y. So in fact, if it is a bipartite graph, then it should be quite easy that you recognize which part is x and which part is y. And moreover, as long as the graph is connected, this partition is unique. You just pick one, and then everything that is adjacent to this one is going to be on the other side. And everything that is adjacent to the other side is going to be the first side. So you can try to redraw the picture again, but it does not help you too much to recognize the hypercube again. If you draw 1, 2, 3, 4, 5, 6, 7, 8, then you should be able to put all the edges in between. Okay, 1 is going to 5, 6, 8. And then 2 goes to okay, so that's basically the same graph, but you'll realize that on the left-hand side you can kind of recognize the structure better, but on the right-hand side, although you put it as a bipartite graph, you recognize that as a bipartite graph, but it does not tell you much about the structure. But one more thing about the bipartite graph is, in a bipartite graph, there is no odd cycle. Okay, so for example, you can move from x and y and x and y and x, y, and come back with x, right? You always go with x, y, and come back with x. What is the length? The length is always even, because you have to come back to the x side. Right, so inside the bipartite graph, there is just no odd cycle. And there is a theorem saying that a graph is a bipartite graph if and only if it has no odd cycle. So it is the equivalent condition. Okay, so you can see that on the left-hand side, the graph does not contain any odd cycle, and it is also not hard to show that if you don't have odd cycle, then you can keep labeling it as xy, xy, xy without any conflict. So in the end, you should be able to make a successful partition of the graph. And let me show you what happens if there is an odd cycle. For example, this is a Peterson graph. Okay, and you are wondering if the Peterson graph is a bipartite graph or not. So what you can do is, again, let's say this is x. And so all the neighbors of x are in the part of y. And now you can say all the neighbors of y is going to be in x. So this is x, and this is x, 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 x. Right? And you realize there are some trouble happening because you got two x happening together. And the reason for this x, the reason of this phenomena is because that we start from x and say this is y, and then this y tells that the next vertex is x, right? And I also start from x to say this is y, and then this vertex says that the next one is going to be x. and we got a even path and goes to the other even path, but in the end they have an edge in between, so this becomes odd. So in fact, the odd cycle is really the only obstacle, the only difficulties for you to do this kind of labeling. If there is an odd cycle, then the labeling will fail. If it does not contain an odd cycle, then you will successfully find a good partition of the graph. So that's just kind of the flavor of that, and because we are not really in the graph theory course and we don't bother to really prove that. So just try to remember they are equivalent. Now there is another interesting thing about the adjacency matrix. So suppose A is a bipartite graph, and G is the bipartite graph, and A is its adjacency matrix. So what do we have is G can be written as X and Y, and all the edges are in between. So we can partition the matrices into this form such that the first few rows just corresponds to the X, and the last few rows are corresponding to Y. And you know the ones on the adjacency matrix are the notation for the edges, but there is just no edges in between. So X to X is just a 0. And if you want to emphasize the size, it is the 0 matrix of cardinality X. And on the right hand side, you also got a 0 matrix. And all the edges are in between here and here. Right, so we just write that as the B matrix, and then this part is the B transpose, because one side is talking about Y goes to X, the other is talking about X to Y. And the point is that X and Y does not necessarily have the same cardinality, so B is not necessarily a rectangle. It's not necessarily a square. So, for example, we can see this graph. This is called K14, and its adjacency matrix look like 0, and this is the first vertex, 1, 1, 1, 1, goes to all the 4 vertices, and a lot of zeros here. So the partition looks like here. You got a 0 matrix of order 1 and a 0 matrix of order 4, and the B matrix is all ones matrix. Okay, so later on, all we want to know is that what is the property of this kind of matrix. So suppose A is a matrix that looks like a 0, 0, and the B transpose. Now here is the key. If there is a vector called X and Y, okay, whenever I write it like this, means X is a vector that is of length like this height, and Y is a vector of the length of this height. So whenever we multiply this A times X and Y, then it means 0 times X plus B times Y. So whenever we have this kind of vector, and if it is an eigenvector, this is an assumption, then this is equivalent to the following condition, says that 0x plus bty is equal to lambda times x. So I'm going to erase the 0 part. Okay. And on the other side, we also got b times x is equal to lambda y. So the left hand side and right hand side, they are equivalent condition. They are just on the left hand side, we are writing the matrix form. On the right hand side, it is writing that based on each row. Now, we have an interesting observation at this point. Let's focus on the equation on the right hand side and replace y by minus y. So this is what we are going to do, y, and switch to minus y. And what do I mean is the following. Now b times minus y is supposed to be minus lambda x, right? And for some purpose, I'm going to make a parenthesis here. Now, b times x is again equal to lambda y, but we can make it equal to minus lambda times minus y. So, of course, if the equation on the top is true, then the equation on the bottom is also true. There are equivalent conditions. But now, if you move to the left-hand side, you can know that this is the same as the matrix equation saying a times xy, a times x minus y is equal to minus lambda times x minus y. So as long as you got an eigenvector which has the form of x and y, then you can flip the y side into minus y, and then it is again an eigenvector, but the eigenvalue is going to be different. So this is the theory. If A is a symmetric matrix of the form B transpose, and notice that this B can be any matrix, any real matrix, rectangular matrix, then the eigenvalues, the spectrum of A, well, let me make it more precise. Then lambda is an eigenvalue of A, if only if minus lambda is also an eigenvalue of A. And moreover, they are going to have the same multiplicity. Because if you have an eigenvector, you can transform the eigenvector into the other side, and it is a one-to-one correspondence. So it has a nice symmetric structure that lambda and minus lambda always occurs simultaneously as an eigenvalue, and their multiplicity are going to be the same. So let me give you some example, and don't bother to, I will just let you know what is the eigenvalues, but okay, this is a result that is not so easy, but if we have a Pn, a path on n vertices, then the result is saying that the spectrum of A of Pn is equal to 2 times cosine n plus 1 and then k pi, where k is running from 1 to n. And it looks ugly, but basically this is what it means. Okay, this is a real line, and here is 0, here is 2. So we draw a hemisphere or a half circle on the top. Now I partition the pi, partition 180 degree into n plus 1 parts. And now this point is k equal to 0, which is not what we wanted. This is k equal to n plus 1. This is also not what we wanted. What we wanted is this part. This is k equal to 1, n plus 1 over pi, and this is 2 pi, to this side. So you will see that this is the eigenvalues. There are the cosine values for some angles, and it is symmetric along with the 0. Okay, if you got the left hand side, you got the right hand side. And let me give you one more example, which is K14. This is a bit easier. And if you really calculate the eigenvalue, in fact, now you know how to calculate the characteristic polynomial, right? So you should be able to know what is the eigenvalue. But this eigenvalue is equal to -2, and then 2 zeros, and 3 zeros actually, and a +2. So what you have seen here is the zeros here is one of the eigenvalue, but it happens 3 times. There is -2 and +2, and each of them is an eigenvalue of multiplicity 1. So the eigenvalues is going to be symmetric along the left hand side and right hand side, along the origin, the 0. The only possibility that you got an odd number is when the eigenvalue is equal to 0, right? By that I mean, if you have -2, then you got a +2. They are a pair. But the only thing they are not a pair is the things in the 0, because minus and positive, they are the same part. So it is possible that an odd number of vertices, a graph with odd number of vertices, is a bipartite graph. But in that case, it must have a 0. So this is kind of immediate consequence. So if G is bipartite, and the number of vertices is odd, then you know it is impossible just be non-zero minus eigenvalue and positive eigenvalue. There must be 1 0. Then 0 is in the spectrum. And equivalently, the determinant of A is going to be 0. So interesting, right? It is just based on the number of vertices, and you can tell something about the eigenvalue. Okay, so let's do the last part. And the last part is try to focus on the converse of our statement. So what we have done is, if G is a bipartite graph, and then we will know that the eigenvalues are symmetric to 0. And if lambda is an eigenvalue of multiplicity m, then minus lambda is also an eigenvalue of multiplicity m. Now we want to show that the converse is also true. So suppose one graph that we don't know what is the graph, but suppose we know the spectrum of the adjacency matrix, and we know it is symmetric to 0. Then G itself is a bipartite. So that means just look at the spectrum, then you can tell some property of the graph. That's kind of the spirit of the spectral graph theory. So now we are going to see why this happens. So what happens is, like, the eigenvalues looks like this, right? You got some zeros, and you got some lambda 1, lambda 2. Maybe they have some different multiplicities. So this is 0, and maybe you got lambda 1, lambda 2, lambda 3. So what is the characteristic polynomial? The characteristic polynomial of A, it can be written as minus x to a certain power. It depends on what is the multiplicity here, and make a product of lambda minus x and minus lambda minus x. And now you can run through all the lambda which is greater than 0. So if the eigenvalue is symmetric to 0, then you can write the characteristic polynomial into this form, and the later part can be combined. Then it looks like minus x to certain power, then the product of lambda squared minus x squared. X squared minus which side? X squared minus. Okay, let me write that again. X squared minus lambda squared. I believe so. So you will realize that this part is an even function. And what does that mean is this characteristic polynomial is equal to S0 minus xn plus S1x plus something up to a certain point, which is equal to minus x to the you got xk, right? So xk and s m minus k, and plus 0, 0, 0. So there are lots of 0 in the end, and then this part is going to be even. Okay, so that means S1 is equal to S3 equal to something is equal to I plus 1 is equal to 0. So all the odd terms are going to be equal to 0. Suppose the eigenvalues is symmetric to 0. Okay, so that's the consequence, and then we're about to make the conclusion now. S1 is equal to 0. That's straightforward. That happens all the time. And S3 is equal to 0. That means there is no triangle. Right? But now, what about S5? Why S5 is equal to 0? You see, 5 can be equal to 5 or equal to 3 plus 2 or equal to yeah, that's all, right? You cannot have 1. So it is impossible. So it is the only case is that you got the 5 cycle or you got a 3 cycle with an edge, right? But we know there is no 3 cycle. There is no triangle, and it is basically just counting the 5 cycles. So S5 equal to 0 tells us that there is no 5 cycles. And for the same reason, you can see S7. 7 can be a 7 cycle or a 5 cycle plus 2 or 3 cycle plus 2 plus 2 or plus 4. Anyway, it is not going to have a shorter odd cycle. You don't have a cycle of length 3 or 5. The only possibility is that you got the 7 cycle. It only counts the 7 cycle. So 7 equal to 0 says that there is no 7 cycles. So when you keep going on, you will see that, okay, this whole equality equal to 0 will tell us that G has no odd cycle. And that means G is a bipartite. So, in conclusion, a bipartite graph will have its eigenvalue symmetric to 0. And the other way to say this behavior is that you can see the characteristic polynomial. The characteristic polynomial has S1, S3, S5 all equal to 0, and there are maybe some zeros in the end. But the key is that all the odd terms are equal to 0. And now by using these odd terms equal to zeros, you will realize that, okay, there is just no odd cycle. So G has no odd cycle, so G has to be a bipartite graph. So all the conditions are equivalent.